Hello friends, welcome. Let's get started with class 6 chapter 10th of science, which deals with motion and measurement of distances. So before we start about understanding the distances and their measurement, let's take a common example from our life. So this was a summer vacation. So all of you must have gone somewhere, maybe to nearby places or to far off cities. One of the things that you would consider while planning your vacation would be how far the city was. Depending upon the city, right, how far it is from you have to go, you'll plan your vacation and you will choose the appropriate means of transport. Whether you have to go, you can only go by cycle, or you have to take a car, or maybe you have to take train or airplane, right? That decision depends upon how far the city is, right? So unless and until we know the distances and we are able to predict the time it would take to reach the other place, how would you plan your vacation? You can't really do that. And therefore, we need an accurate way, a method of measuring these distances. Previously, in olden days, in ancient time, man was not very fortunate to have all these means of transport at his convenience. These were slowly and gradually developed, starting from the invention of wheels. And before that, man was only walking, or he was using animals, he was riding on animals. After the invention of wheels, we then invented petrol engines, and now we are talking about rockets, electric vehicles, so on and so forth. The various means of transport, let's delve into that a little bit, because questions are sometimes asked from here. They are of many kinds, right? They can be categorized into three main kinds: land, water and air. Land transport, these are vehicles which ply on land. Some of them require corridors like dedicated rails or roads for vehicles, but others are very unstructured. They can go anywhere. For example, the tanks that are used in defense. Again, water transport means can either ply on the ocean, which like intercontinental transliners, right, the large giant ships, or they can be smaller inland vehicles, water transport vehicles, boats, right, smaller boats, and these ply on the rivers. Air transport is relatively recent, and of course we know this includes airplanes, helicopters, rockets, so and so on. Now of course the fuels that are used in these, right, so these vehicles, they have to be powered somehow. So they can be powered using various means. We already know that things like cycle or bullock carts, they are either human powered or animal powered, right? So if you are doing a lot of cycling, I'm sure you will feel hungry, because the cycling actually uses your energy. It is powered by your energy. Most of the vehicles that we see today, of course, are powered by petrol and diesel, and we know that fossil fuels. Coal is not used so much. During industrial revolution it was used, but is not in use so much for powering the vehicles. But even these, we are trying to get rid of our dependence on fossil fuel for transport, and now we are talking about renewable energy, for example solar cell cars, or we are even talking about electromagnetic propulsion. So this propulsion would be done using electricity and magnetism. So examples are of course electric cars, which are now a reality, or levitating bullet trains, right? So these, using electromagnetism, they rise a little above their track, so they can run very fast. Ropeway, these usually you find in the tourist places, these are also powered by electricity. Now of course when we talk about means of transport, we cannot really ignore the fact that some of them are faster than others. So for example, the cycle that you use is slower. You know that the cycle is slower than the car, and of course car is slower than an airplane. So we cannot really ignore the speed of the mode of transport that you are using. A cycle perhaps is adequate if you are going from your home to school, but it's definitely not adequate if you have to travel, let's say, from Bombay to Delhi, right? So here are the means of transport, right? Different vehicles arranged in the order of their speeds, right? So it's in increasing speed. Now with that, we cover the basics of transport, and the means of transport, and we come on to a very important section, which is measurement. Now, even before we start with the measurement of distances and lengths, right, that's what we are here for, we need to understand what measurement actually means. I mean, what indeed is measurement? So if you think about it, what does measurement do? Measurement compares an unknown quantity to a known quantity. So for example, I really don't know the length of this table. I don't really know how big this board is, and I want to find it out. So one of the simple ways I can express this in terms of known quantity, right, is let's say my hand is span, right, this hand is span, I know how big this is. I can express the length of this table in terms of the hand span. So let's see how many can I fit. Roughly 3. So what have I accomplished here? I have accomplished the fact that now I have this length expressed in terms of 3 hand spans. Now whose hand spans? Of course mine, right? I mean they are my hand spans. Yours might be different. A small kids might be different, right? So the hand spans are of course not standard. They change from person to person. But when I know this, when I know that this length is 3 hand spans, suppose this particular board breaks, like is broken, and I want to get a new one from the market. What can I do? I just have to go to market and measure the various boards, and I have to find one which measures 3 hand spans. I can get it and it would perfectly, I'll get it and it would perfectly fit this space. Right? So with that, even that rough measurement, I have accomplished something. Right? But indeed, that measurement has 2 aspects. If you look at it carefully, there is a number which is 3, right? So I am saying it is 3, and what 3? 3 hand spans. And of course, there is a problem with this measurement too. Suppose instead of me going, there is a small kid which goes to the market and gets this. Instead of I didn't go, but the kid went and got me a new board when this one broke down. So the kid, I would tell him that, oh, get me 3 hand spans big board, and he would get a board which is 3 of his hand spans. So it might not come out to be this big, but it would come out to be only, let's say, this big, right? It will come out to be a little smaller and might not fit the space. So the problem with this unit, our unit of hand span, is that although it being convenient, it is very convenient, but at the same time, it is not standard. Unless and until I go to the market, unless and until I measure it with my own hands, there is no way for this particular length to come out the same, right? Length of 3 hand spans to come out the same across the world. There is no way to for me to do that unless and until I measure it using my hands. Right? So that's why we call it non-standard. So in olden days, like so of course we already talked about this. So the measurement includes 2 things. One is a number, and second is what does that number mean. Right? Suppose I am carrying a bag with me and I tell you that there are 3 in that bag. So that 3 sounds incomplete. You want what 3, right? I mean 3 apples, 3 mangoes. What is that 3? So that 3, that incompleteness goes away as soon as I say maybe 3 apples. So I need a unit. Right? This is called a unit. What does the unit gives the meaning to this number 2? A measurement always has these 2 things. It has a number and a unit. In physics and science, units are very important. You should never ever forget these, right? I mean, even in common life, units are important. But we need to have this in front of our numbers. So now, when we are into the subject of units, let's go a little forward and see what ancient men, what the earlier times, right? In historically, what kind of units were used. So like I said, people in ancient times didn't have to be so accurate. I mean, what did they have to do? They were into farming, so they had to measure the sort of area of their farm, and for that it was sufficient to know the rough measurements of the length and breadth. And with that, they were able to estimate how much seed, how much water, how much labor would go into farming this land, right? So they were able to do that just with approximate measurements. And conveniently, they would use their body parts for doing this such kind of measurement. So for example, in ancient Egypt, one of the units which was used is known as cubit. So what is cubit? A cubit is the length of the arm from the elbow to the top of the finger. So this is 1 cubit, right here. Similarly, there were other lengths too. For example, a fathom was the length from arm to arm, from hand to hand, when the arms were fully outstretched, right? So this was 1 fathom from here to the tip of the other finger, right? Shown right here. Similarly, hand span, I told you this was convenient, and we indeed did some measurements. A width of a thumb was also used as a measurement. It's approximately an inch, right? So inch was derived from here, and we still use it. For example, in your phone, there is something called a thumbnail, right? In the gallery, if you are taking pictures, there are thumbnails seen there. Stride length was also used, that is the length of one stride when the person is walking comfortably. Foot is of course a unit from which we derived the modern unit of feet. Now, of course, the problem with these units, like we said, was they were non-standard. They changed from person to person, so they were not really very applicable across the board. Of course, another problem with primitive units was not only did they change from person to person, they were not consistent across the world. So, for example, the units used in Egypt were cubits, while at the same time in India, the units that were used were finger, right, the length of a finger, or mutti, the length of a fist, right, the width of a fist. So, of course, there is no way to compare an angul to a cubit, right. So, person from India, if he is trading with a person from Egypt, they don't even have a common language in terms of measurement, in terms of units. So, this was the big problem. Like imagine in Gulliver's Travel, if the people from Lilliput and the people from Giant Land, they were trading, and someone in the Bobdy gang, which was the land of giants, ordered, let's say, a wheel for his bullock cart, right? A wheel for his bullock cart. So there was this giant bull for which the wheel was ordered from Lilliput, and the measurements were given in terms of units like body parts. Like for example, 3 hands, right? So 3 hands wide. So the person in Lilliput the small person would use his hands, right? And the wheel that would come out would be really small. So indeed, these kind of problems were indeed faced by people when they started trading and traveling across the world, right? Even the units of time like days and those things were not very clear. Days, hours, seconds, those were not consistent, and people had lots of problems. So with increasing globalization, with increasing trade, what happened? People from around the world, especially traders and common people, they realized that now we have to come up with consistent set of units. So they tried, and ultimately these 3 units were devised which went into use across the world. So there was some level of standardization which started now happening. One of these units, right, is MKS. So for each unit, the first letter denotes the unit in which, for each of this system, right, the first letter denotes the unit of length, second one denotes the unit of mass, and the third one denotes the unit of time which was used in the system. So for the first one, which we call as MKS, the length was measured in meters, mass in kilograms, and time in second. For the second, which we call CGS, length was in centimeters, mass in grams, and time in second. The third one, which is FPS, length was in foot, mass was in pounds, and time was in seconds. So with this level of standardization, like instead of having thousands of different kinds of systems of measurement, we were now consistent, little bit consistent. Across the world, we were using only 3 main systems. So maybe common people were happy, okay, that you can travel, maybe you just had to do some conversion, but that was fine with common people. But for scientists, this was not enough, because scientists really needed the accuracy, right? They needed the exact same units across the world to be able to share their work. Because scientists from India maybe wants to share his work with someone in United States or someone in Britain. They really needed the exact same unit. They needed to speak the same language. So scientists then thought that, okay, let us devise a new set of units and we'll all agree that to use that. This is known as SI units or Système International. It is a French word. The units are basically derived from the metric system which was used in France. Okay, so these SI units are very important, but we'll not cover all the details of SI units now, but instead we'll focus on the 3 units, second, meter and gram. So the SI unit has 7 base units. What does it mean by base units? So scientists and physicists from around the world, they said that we can measure all the things in this universe. Everything that is measurable can be expressed in terms of these 7 units. That is what they claim, that is what they thought, right? And therefore these 7 base units are used to make all kinds of other units used for measurement in physics. Ampere, Kelvin, which is for temperature, ampere is for current, second, meter and gram, which are respectively for time, like length, and gram is for the mass, candela, which is for light, and mole, which is for quantity. So these are the basic 7 units you need to remember: second, meter and gram. Those are important. Focus of this chapter is of course measurement of distances. So let's just give it a minute and define the meter. All these units in the SI system, right, all the 7 base units in the SI system have a definition, have a physical meaning, right, that it means something. So what does it mean by 1 meter? What is the physical meaning? When I say 1 meter, what does it mean physically? What does it mean in the world, in the real world around us? It means the distance which is traveled by light, right? So light always travels at constant speed, and this light in vacuum, the distance that is traveled by the light in vacuum in 1 by 299,792,458th of a second. So in this much part of a second, the distance traveled by the light in vacuum is known as 1 meter, has been defined as 1 meter. So this is the physical definition. It remains the same across the universe, right? Because light, the speed of light is constant, the speed of light in vacuum is constant. So this 1 meter does not change anywhere in the universe. It remains same, which is a kind of a big deal, right, if you think about it. But of course, just by defining a meter doesn't do us that much good. I mean, I'll tell you why, right? Because the thing is, a scientist, a physicist is obsessed, and he really wants to measure everything, right? I mean, this is what the job of a physicist is. He wants to measure the distance between atoms, which are really, really small, tiny, right? These distances to very large distances, intergalactic distances. He wants to measure everything from the smallest scale to the largest scale. And of course, all of that cannot be done or cannot be conveniently done by just using 1 unit meter, right? I mean, you'll have to write sometimes very, very small numbers, and sometimes you'll have to put in very, very large numbers. So of course, that doesn't work very well. So SI unit, the system of SI gave us another thing, right? Another convenience, which are known as prefixes. So in addition to these units which are right here, for example the meter, we have certain prefixes which can be put before the units to change their meaning. So the meter is the base unit and this is the prefix. For example, a kilo makes the meter 1000 times bigger, right? So a meter is maybe this much and a kilometer is 1000 times bigger. So it is multiplied by 1000. The length of a meter multiplied by 1000 makes a kilometer. So that's what a kilo means. There are other units there are other prefixes which also multiply their respective base units by a certain factor. So here are those. Of these, you should remember kilo, hectare, deca, deci, centi, milli, right? You should remember these. So our base unit sits somewhere here. So this is our meter, which would sit right here. And if I go down, I am making smaller units, right? I am making smaller units. For example, a centimeter is 1/100th of a meter, is 100 times smaller. On the other hand, a kilometer, like we said, is 1000 times larger. So when we go down, we are making smaller units, and when we go up, we are making units larger, right? There is a distinction here, right? So I'll tell you in 1 second. So for example, now let's try to convert 5 meter to centimeters, right? We are trying to convert meter to centimeters. So how many centimeters would be there? Remember, a meter or a centimeter is 100 times smaller, right? A centimeter is really small, whereas meter is large. So to measure the same distance of 5 meters, I would need a large number of centimeters. How much large? Of course, 100 times as many, right? So the same distance of 5 meter would, instead of being covered in 5 meters, would now be covered in 5 into 100, which is 500 centimeters, right? So when the units, they become smaller, right? The unit is becoming smaller, a centimeter is smaller, the corresponding value increases by the same factor. Similarly, when the unit becomes larger, as we go up, for example, kilometer, the corresponding factor is divided, right? The corresponding value is divided by the same factor. So this would be 5 by 1000 kilometer. Right? Hope this is clear. These questions are asked, conversion from one unit to another, and it is important that you understand that. So now moving on, once we understand what are the units and how do we express the measurements, let's understand how to do good measurements. Right? We are in this chapter only dealing with measurement of distances or lengths. So let's focus on that and try to do some good measurements. So here I have a scale which can be used to measure the quantities, right? Maybe you cannot see the gradations here, but there are gradations, and if you look closely, right, maybe you can get your own scale and see what is there. So there are some larger marks which are 1 centimeter apart. So these larger marks are 1 centimeter apart, but the larger marks are then themselves divided into 10 smaller marks. And of course, we know that this is centimeter, so 1/10 of a centimeter is 1 millimeter. Therefore, the smaller marks correspond to 1 millimeter. Since there are no markings smaller than 1 millimeter, I cannot use this scale to measure lengths less than a millimeter, right? So this is the limitation in accuracy. So this scale is only accurate to millimeters. I cannot go beyond a millimeter. So that is one thing that you have to measure it. The accuracy of the device you have to take into account. Now when you are doing the measurement, you have to keep the thing that you are measuring. For example, if I want to measure this, close to the instrument using which you are doing the measurement. So in this case it's a scale, so I will keep this remote close to the scale and then do the measurement. That's one thing. Second thing that we have to be careful is how do we start and end. So the start of this remote I'll align with the 0 and end I'll see where it ends, right? So it ends at 9, therefore the length is 0 to 9, which means 9 centimeters. So this remote is 9 centimeters long. On the other hand, if this scale was somehow broken, the front part was broken, then I can start from any other place. I can start from, let's say, 2, and then my measurement will go on till 11. So if I start from 2, the measurement ends at 11. To compute the length, what I do? End measurement, which is 11 minus 2, which is equal to 9. So the length then comes out to be again 9. So with that, we come to the last important thing, that is, when you are doing the measurement, you have to reduce the parallax. You have to view the measurement or take the measurement from the top, right? That is what you have to do. So I have to read the scale like this. If I read it like this or read it like this, I'll end up with inaccurate measurement. So of course, even with all the precautions and taking all the care in doing the measurement, errors would still prop up. They'll still come up, and we need to be mindful of that. And we'll later on in later classes, in higher classes, we'll study how to actually deal with these errors in measurement. It's important. Now, once we know all the things that we need to do to take the correct measurement, we have to still focus on how to get the right device for measurement, right? We still need to choose the right device. So for example, if I want to measure the circumference, right, of this cylinder, I cannot use a scale because the scale really won't bend, right? I would break the scale, but it probably won't bend. So to do this measurement, I can use a piece of thread and take the measurement, right, wrap it around this cylinder and measure its length, its circumference in terms of thread length. When I have this thread length, so this much thread length covers the entire circle, right? This entire circumference is covered in this much thread length. Once I know that, I can then take this thread length and put it in front of the scale and get the length of the centimeter, which get the length of the circumference. So I'll put it close to the scale and it comes out to be 20. So of course, that is what we have to do. This is what the tailor does when he does the cloth marking or when he takes the measurement of a person, because scale is not convenient for those cases. There are several other devices also which are used for measurement, right? I mean, think about it. I even have this large giant scale to do some measurement. The type of device you choose depends upon the shape and size of the object you want to measure. Of course, for measuring distances between cities, I really cannot use this 30 centimeter scale. It will be terribly inconvenient. And of course, the accuracy also determines the device I'll use for measurement. Now, once we have understood the different devices and measurement and its types and the accuracy, we now need to move on to the last point, thing in this chapter, which is the types of motion. So there are various things around you which are in motion, right? For example, the ceiling fan is in motion, the car, your cycle, when you're riding it, it's in motion. While there are other things which you don't really expect them to move, right? For example, buildings or mountains, if they started moving, I mean, that would be a really, really bad thing. So there are certain things which move and other things which don't really move. The things which are move have various kinds of motion. The most common of this, or the most simple of this, is translatory motion. What does it mean? Translatory motion means that the entire thing is moving. Right? So for example, the ceiling fan, although it is moving, right, it is rotating, but it is not undergoing translatory motion. It stays at the same place and is rotating. So there is movement in the fan, but the fan itself is not moving from one place to another. So it is not undergoing translation, which means that translatory motion happens when the thing themselves move, they change their location, they change their place. Of course, there are several kinds of translatory motion. One is when the things are moving in a straight line. For example, cars moving on a straight road. That is known as rectilinear motion or simply linear motion. Other kind of motion is curvilinear, which means things which are going in round and round. So for example, Earth revolves around the sun. That is curvilinear motion. That is right, revolving around the sun is a curvilinear motion. Rotation of the Earth itself is not really translation, right? Because it is rotating on its own axis. It is not changing place, it's changing its place. The entire body Earth is not changing its place. Of course, then we can have random motion too. For example, ants, I mean, they are typically, if you see them, they are undergoing kind of random motion. Then, second kind of motion that we just discussed, rotary or circular. This happens when things are moving around an axis. So for example, let's take the example of Earth. Earth rotates. So the Earth is rotating. The rotation happens around this axis. Your fan also is rotating. The rotation is happening around an axis. What does the axis really mean physically? So the axis is the line along which the entire thing is moving. The line itself does not move. Remember that. So if you look at the axis, if you touch a point on this axis, that point is not moving. But the entire thing, rest of the stuff is moving around the axis. So rest of the things in the body, rest of the particles, points on the body are moving around the axis, but the axis itself is not really rotating. So of course, depending upon where the axis is, there are two kinds of motion. One I just showed you, the rotation of the Earth around the axis, where the axis lies internal to the Earth. It is passing through the Earth. Fan is another example. The axis around which the fan is moving, or all the points on the fan are moving, the axis lies within the fan. The second kind is revolution of the Earth. For example, when this is revolving, this pendulum, the axis of rotation, the axis along which this revolution is happening is external, is outside the pendulum, this ball itself. So the axis is outside and the ball rotates around the axis. So in this case, we call it revolution, right? In the other case, we call it rotation. Of course, rotating motion can be both. It can either be rotation, right? Circular motion can be either rotation or it can be revolution, and revolution is of course translatory motion because the entire body is moving. Now the third kind of motion which has been discussed, right, which we have to know in this chapter, is rolling motion. So think about this. Let's take an example of this yo-yo. This is a yo-yo. It goes up and down. So one of the things that we can do with this yo-yo is actually this rotation, right? So this yo-yo can rotate and the axis of this yo-yo passes from here and it is rotating about that axis, right? I am trying to keep the axis at the same place. So it is rotating about that axis which is passing from here. Now when this if I leave this yo-yo and allow it to go down, you'll notice that not only is it rotating along this axis, but it is also going down, right? And then coming up. So there are two kinds of motion happening here. One is this circular disc is rotating along the axis, and at the same time the axis itself is going up and down, right? This entire body is moving up and down. So that kind of motion where the axis, the things are moving along an axis or rotating around an axis, and at the same time the axis is going, right, somewhere, is translating, is known as rolling motion. So for example, if you take a look at your car, what is happening? The car is traveling, the wheels are rotating along an axis, but at the same time as the car moves, the axis itself, the entire thing, the axis including the axis of the wheels is going forward. So this kind of motion is known as rolling motion. A football is undergoing same kind of motion. It is rotating while at the same time it is translating. Right? The axis itself, the axis of rotation itself is translating. Now of course the second kind of motion that we need to understand is oscillating, is periodic and non-periodic. So all of these motions can be either periodic or non-periodic. A periodic motion repeats after certain instance of time, after certain time. A non-periodic has no such repetition, it's kind of random. So among the periodic motion, one of the simple ones is vibration, right? So you must all have done this. If you take a scale and then, right, just you can make it vibrate. So what does, right, this is vibrating. So what does vibration mean? Vibration means that this scale itself is moving up and down, up and down, up and down, right? It's not translating, it's not going anywhere. It is just moving, it's just vibrating. The same thing happens when you are due for your viva. So if you are sitting in front of your supervisor and you are giving viva, you will start vibrating. You're not really going anywhere, you're standing there and you're just vibrating, right? So that is vibration. Now another kind of motion is oscillation. So oscillation, what does it mean? It means it means that this entire body is actually translating. So this is oscillation, right? If you notice this pendulum, it is periodic first of all, and second, it is going, the entire pendulum is going back and forth. So it is translating, it is undergoing translatory motion, and this kind of periodic motion is known as oscillation. The third one is reciprocating motion, which is again something, right? If you have noticed, the carpenter in olden days, actually they used saw to cut the wood, and this to and from motion is known as reciprocating motion. Rotary motion we have already discussed, as in the case of earth, right? So that earth, sun, etc., they undergo periodic motion. Now one of the things which you should intuitively understand, which has been introduced in your book, is that of speed, right? It has been intuitively introduced, so it is, formal definition is not given, but you should understand that to cover the same distance, different things might need different amount of time. So for example, this is 30 centimeter distance, right? This 30 centimeter distance, for example, using a cycle, it would take longer, and to cover the same distance using a rocket, you know, it would take shorter amount of time. So the thing which takes shorter amount of time has larger, intuitively we understand it has larger speed. So now if we want to make this speed, the concept of speed formal, how are we going to do that? So the speed is defined as the distance which is covered in 1 unit of time. So for example, if a particle covers, if a point covers this distance of 0 to 30 centimeters in 1 second, its speed becomes 30 centimeter per second. So in 1 second it is covering 30 centimeters, therefore the speed is 30 centimeters per second. Of course, we will be covering very soon other lectures, other chapters in science, so do stay tuned with us, do subscribe. If you have comments or questions, or if you want to give any kind of feedback, you can put that below in the comment section. I personally look at those all, and I would of course take your suggestions very, very seriously. Thank you very much. Good luck.